Good afternoon to all of you. So we talked a lot about data and the signatures of climate change, global warming, etc. So we also looked at, for example, came across the words called trend. It is increasing, decreasing, all that. So once you have the immediate question is, once you have this data for a long time frame, how do you determine what is called as the trends? And how do you differentiate this due to that or this or any other factor, etc. So in this practical session, as requested by Vijay, I will try to discuss a few things about how to determine a trend in a geophysical variable or a parameter, and what are the normally what you see in a signal or in a data, how do you decompose them, etc. So the first basic difference that comes to that we should know is the difference between what we call as an anomaly or a trend. So an anomaly is what is a deviation from what is standard or what is normal or what is expected. For example, a low temperature is expected in winter, as we all know now. But when this thing occurs in the summer month of May or June, then it is an anomaly. If it occurs every year after year, then it is no more an anomaly, but it happens, for example, like a transient response, then it is an anomaly from the normal trend that we know. Okay, now, for example, examples of anomalies. Here I wanted to highlight. So if you look at the anomaly, for example, it would have been almost near to zero. This is a temperature in degrees centigrade, and this is only due to volcanic eruptions that occurred in the last 150 years or so. The effect of this on the temperature. So you see that for example, it goes all the way up to minus 1.5, and then it comes back up. And then you see these signals only when there is a major volcanic eruption. Otherwise, they are almost near to zero. Okay, so this is a kind of an anomaly. And the same we see in the stratospheric temperature also. Otherwise, you can draw a straight line somewhere here, but you see that sudden burst of or increase in temperature that occurs. Otherwise, it will come to the normal. But please note, even if you exclude this, if you exclude this transient responses and you plot this, you actually see a decreasing trend in the stratosphere. Now, this is a trend, while this is an anomalous or transient response. So, trend represents, or it means, general movement of a series over an extended period of time, or is the long-term change in the dependent variable over a long period of time. Or simply put, trend designates a change. So when you look at the data, the time series of data for several years or several seasons or whatever it is typically made up of 3 or 4 components. So, for example, which is shown here in black is the trend line. The total increase or decrease is actually called as a trend. It changes over time. It is changing, like you can see, from higher to lower to higher, but it is not periodic. So that is called as a trend component. If you look at the seasonal, so this repeats year after year and season after season. So this is a seasonal thing. So when you are trying to define a trend or determine a trend, if the data is a seasonal thing, you have to remove or de-seasonalize the trend by looking at the measure, by getting the averages and then putting the average back into the data and trying to get the residuals and then trying to plot the seasonal trend. Now, there is the next one is called as a cyclical. which is a long-term component in the data, but it is not necessarily periodic, but can have a similar pattern. For example, climate data. You can say that, well, the temperature generally in winter is colder versus it is generally high in summer over India. Now, this is a cyclical thing. It's a even if you look at 100 years of data, you will get this cycle. It's a long-term component. It not necessarily, but can have a similar pattern. Now, the fourth one is some of them are kind of irregular fluctuations. These are random and cannot be described by any other component or its properties. Typically, the values are relatively small and not systematic. So, if you look at the data as a function of time, and these are the four things that you will see immediately when the data is put to it. Now, the changes that occur over this data, during this data, could be an additional thing or could be the effect due to multiplicative nature. So let us look at the data, for example. This you can consider as number of years, any data, any number, whatever it is. So you see that the seasonal component is constant. Just like I said, the weather, if you take winter, summer, etc. But overall, the values are increasing. But please note the seasonal component is not changing. So this can be this series, this time series can be decomposed into first as a seasonal component, and then the trend component. Random is the unsystematic component that has like fluctuations that are really irregular. For example, if you take this and this, you see that it is not, this peak is not as sharp as it happened. This peak is not as sharp as it happened in the previous and the succeeding year. But apart from that, this can be clearly classified as seasonal plus trend plus small random. Now contrast this with the other data. This is again a function of time here. So you see that first what is visible is that there is an increasing trend. But please note the seasonal trend itself is changing. And the seasonality increases in magnitude when the values increase from, let us say, 300 to 500. So this means that this is initially season is not there, the trend is there, and then the random thing is there. So this will be a multiplicative effect in the trend. So seasonal multiplied by trend by the random effects will give you this multiplicativity in the trend in the sigma. Now suppose, let us do this with the data that give as an example. So the top one is the data that is similar to what you saw just now. And then first we do the seasonality. So seasonality, you see that it is, so we are now removing or decomposing the trend into seasonal, random, and the trend or long-term trend. So first what we did is take out the seasonal thing. So you see that this is there. It is repeating year after year. So from this, we actually took this one. And so when you take this, the trend aspect, so as we know, initially there is not much of a seasonality. So it's almost a flat line, and then it starts increasing as the graph is showing here. So you see a positive increasing trend. Now, this random nature or the unsystematic values are also plotted here, which are residuals. This can be both positive and negative. This is which are leftovers after dividing the time series by the trend and the seasonal components. So this can lead to changes or deflections either in upward or in a downward direction. So for example, I revert back to this same graph that we saw about an hour ago. We have an observed trend that is documented. So we put in first two species, and then we see that this is not there. So If you ask, for example, a trend in this red and the blue component, it is almost a straight line, just like the signal that we saw before in the volcanic thing. But you see the observations, they are increasing. Okay, about the rates of increase, decrease, etc. We'll see in a few minutes. And then what you do is that we put this greenhouse gases, aerosols, and ozone, and you see that this is captured. So there is this is again a difference between what is the normal thing versus the increasing trend. Putting these components into this one, we are able to simulate and get the trend. This also is an indication of the decomposition. So this one, for example, we put in solar radiance and volcanic eruptions, and we could not decompose this trend. But the moment we put in also added to these two changes in the greenhouse gases plus aerosols plus changes in ozone, we are able to simulate this. So this is actually a decomposition effect that we are able to see in the trends. So coming back to this same global mean temperature thing. So overall, for example, in the last 150 years, it is an increasing trend. So if you look at this graph, for example, the trends are not uniform. The trends are different at different locations depending on what the temperature was and how it changed. CO2, aerosol, ozone concentration, these are all changing. Because of that, the trends at certain locations are stronger versus some locations it is weaker. So in this case, what we are seeing is actually the global mean temperature. So the entire globe, you convert it into one point and then try to calculate the value. So what you are seeing is, without having to say anything, you can say that, well, in the last 150 years, the temperature has increased. Point number one. Now let us say, like the trend that it can be spatially variant, it can also be a function of time. As a function of time, it can be variant. So what we now do is, we try to get the trend for the 150, 100, 50 and 25 years and see what is happening. So if you go to, instead of 150, you go to 100 years, then actually the trend increases because of the shape of the curve here. Then you make it 50 years, it still increases further. And in the last 25 years, it is still more stronger when compared to the trend in the 150 years. So depending on whether you are looking at the short-term climate variability versus the long-term climate variability, so the trends not only be spatially different, but temporally can be different. And more so in the last 50 years or so, when the temperatures have been seeing an uphill in increasing trend. Okay. So far, so good. Now, coming back to this, we saw earlier also. So the red line, see, this is from June 1st to September 30th. This is the rainfall in millimeter per day. Every day during this monsoon season, June, July, August, September, this is the amount of rainfall that across the country we would have got it. That is the red. This is actually the trend. This is the data based on 150 years of measurements, etc. But what is, so this deviation, you can see either negative or positive is actually the difference with respect to the trend that is happening. So how do we determine that? So we saw first what is an anomaly, and then we saw examples of that in the atmosphere, any parameter taking that, and then how do you distinguish trend and an anomaly? So now let us try to, whether they are additive, multiplicative, how to determine the trend. So for example, the trends in the time series of data of any particular time-dependent geophysical variable can be detected using the linear regression method. Why linear regression? We'll see later. So, which is the equation, you know, a straight line equation, y is equal to mx plus c plus some this thing. So, yt is the unknown statistical variable of which the trend is to be calculated. Xt is an independent variable. It is generally a function of time. day, month, year, etc. Q is the y-intercept representing the value of y at the beginning of the time series, meaning y0. And W is the slope or a linear rate of change in the value of yt. And this is epsilon is the randomness or the noise in the time series. Now, if you take the geophysical variable, I said you can use the linear regression because this method is simple, it is robust, and it need not, the data need not follow the Gaussian distribution or the normal distribution, and is also does not influence if there are breaks in the time series of data. Okay, so so this is less sensitive to the abrupt breaks in the time series of long-term data. So typically, it is not that, for example, if you are looking at the daily trend, it is not that every day you will have the data of a particular parameter. For example, if you are measuring aerosol optical layer, this is a function of the cloudiness in the sky. If it is cloudy, you cannot retrieve the aerosol optical layer. Suppose if you are trying to, if I am trying to determine the trend, then it need not be continuously available. But how do you do that? So this use the linear regression method, because this does not the lack of data does not influence the trend analysis if we use this one. So the other main reason this linear regression method is quite appropriate when the uncertainty or the error or the variability in data is constant. That is what we call as the Gaussian white noise, which is a stationary and then a random thing. And how it is random, in which relating to a process in which every sequence or a sizable sample can be representative of the whole, meaning it is a random thing that is present with zero mean, and is defined by the fundamental property that any two values are statistically independent. So in this case, what happens is the regression then is obtained by assigning the same precision for each parameter, that is by giving a weight of unity to each parameter. So this is when the uncertainty in the data or the variability or whatever you are looking at in the data is constant. Suppose if when we are making the measurement of temperature, we know that the error in making that measurement will be a constant value throughout the year. But there are some measurements in which it is a function of the amount of material or the density of the species that is present in the atmosphere. Okay, in that case, the error is a function of the amount of material that is present vis-a-vis the uniformity. So in this case, we use the assign the same weight of unity to each data parameter and then try to derive the trend. So like I said, it may not be the case. So what if the uncertainty is heteroscedastic? This means that, to put it simply, that the magnitude of the noise or the error is not a constant. In this case, what we do is we assign a weight factor to the parameter that you are for every month, every day, etc. by typically we say this is 1 by sigma square, where sigma is the uncertainty or the variability. When we do this, because it is inversely proportional, lower weight is attached to the parameter that exhibits higher uncertainty or variability, whereas a higher weight is attached to the parameter which shows lower uncertainty. Lower uncertainty means it is more reliable than the one parameter which has the higher uncertainty. So one with lower uncertainty is assigned a higher weight, meaning weightage is given. You would have seen this, for example, if you are consistently performing very well. Let us say, out of the 5 times you have done very well 4 times, and once it so happened that you couldn't write the exam properly for various reasons. So what is done is the weightage for the lower performing, least performing is given to be lower, but the 4 times when you actually got very good marks or you performed very well, a weightage is a higher weight is given, so that the anomalous value in the performance is kind of balanced or evened out, or it is not even taken into account by doing this phenomenon. So now let us say that if you look at this, so this is an example of when the magnitude of the noise is not constant. So let us look at that. What really happens? This is a real-time data that is aerosol optical depth over several locations in India for the past 15 years or so. This is from 2000 to 2010 or so. So what we did is we calculated the trends for three scenarios. One in which the measured uncertainty is less than the variation, that was in Chandigarh, and the uncertainty is similar to variation, and the uncertainty is more than the variation. You see that in all of them, if we had not done the following thing, we had not given the weightage or something like that, vis-a-vis a non-weight, not weighing them, we would have got the same result here, except that the correlation coefficient of determination slightly increases, but otherwise the slope does not change much. Only in Bombay, for example, where the uncertainty is more than the variation, the slope changes a bit. And now this is also reasonable because, like I said, when the uncertainty is more, which means that your weightage is going to be different with respect to certain data than the uncertain data. So that is contributing to the decrease or the change in the slope. So we looked at the parameters that can have spatial variation in the trend, etc. So now let us look at again the aerosol optical depth. Typically, they show a spatial, not only spatial variability, but they show a strong seasonal variation. Typically, a summer high, which is June, July, August, September, versus a winter low. Compare the winter months, it is lower than the summer. Okay. Now, in this case, how do I get the data? So let us look at, for example, the data that is obtained over a particular location. So these are the annual means, meaning day 1 to day 365, I take the mean, and the vertical bar indicates the variation during the year of this parameter, the aerosol optical depth. And then, so 1 year, we'll have one data point with the sigma. And then I try to plot the trend. So here I have plotted the trend. So we saw that as a function of space and as a function of time, the trends can be different. Now we see the third aspect as a function of season, how the trends can be different. So here what I do the same thing. Like first, for example, in blue, which is given in blue, the trend, I determine the trend only for the first 10 years. First 8 years, and then in magenta I derive the trend for the next 7 years, and what the equation that is given in black in the top, it actually covers the whole period. So please note that the trends of the same parameter over a particular location can be different in different time slices. So when we looked at the global temperature data, because the magnitude was always the same, meaning it was always increasing in the 150 or 200 years, only the rate of increase changed. It never got decreased. But in this case, you see the other facet of the trend analysis also, which is at the same location. Because now this is controlled by the amount of the emissions that are there in the atmosphere and not the temperature, which is the inherent property of the atmosphere. So depending on whether the emissions that result in the aerosols, whether they increased or decreased, even at the same location, as a function of time, they can show different trends. So in blue, for example, you see that the trend is positive or increasing. But in magenta, the later half of this decade, you see that there is a decrease. But overall, between 2002 to 2017, you see that the AOD has increased over a particular location. Now, I also told that this becomes interesting because we have a seasonal variation in this. So my immediate question will be how the annual trend, how the season, the trends on the seasonal characteristics contribute to the trends that we see in the annual scale. So what I do is I take I take for every year the winter season AODs, namely December, January, February. Pre-monsoon is March, April, May. Monsoon is June, July, August, September, and post-monsoon is October, November. I take the data and then take the mean of that particular season, particular year, and I put that value here. So at the, for example, if you look at among the seasons, so please remember that in the annual scenario, for the first half it was increasing, second half it was decreasing, overall there is an increase. In winter, for example, all the time it is increasing. So same location, same data, but there is a difference between the season and the year. Okay, that is what is illustrated here. So in the same location during winter, in both the halves, it is increasing, and so the overall trend in black is also one positive, it is increasing. So let us look at pre-monsoon, for example. This is again entirely opposite to the winter this thing, where every time it is decreasing. The shorter two halves and also the longer one, it is all decreasing. The rate of increase or decrease is different depending on the value and the sloping, how it is. In monsoon, it is the same thing that is happening as in the pre-monsoon. All the three are decreasing. Post-monsoon, also it is similar to winter. It is, you can see that this is increasing. So trend of any parameter, any atmospheric parameter that we are seeing, now we know it's a function of time, location, and the data that is available, how it is, etc. Okay. Then the immediate question will be, okay, you said all this, whether how reliable are these trends? Then we should have a measure of, for example, when you say that no, this person is very brilliant, then we say that, okay, how do you judge either by talking and then asking him questions and all that? Then otherwise you say, what is your mark? This one. So you say that, oh, you got 100 in maths, 100 in physics or something. So you say that this is how, I mean, he's very intelligent or smart or whatever it is. So in the same way, you say that, okay, this is increasing or decreasing. I mean, how do I rely whether this is increasing or decreasing? There is a metric, there is a parameter that will determine whether this what you are seeing is a reliable thing or not. So how do you do that? So we have a value that is a measure of the probability that an observed difference, how it could have occurred. So that we call as the p-value. So this is the probability of observation, and these are a set of possible results. And it normally follows a Gaussian distribution. And very unlikely observations are in the fag end, the tails of the distribution. So this is the line that is 95% statistical significance, meaning it is roughly 3 sigma or more than 2 sigma. While the observed p-value or the statistical significance is somewhere here, which means that this is highly reliable. And so this p, the lower the p-value, greater the statistical significance of the observed difference. So the p-value, like for example, here has to be lower. It cannot be here, it cannot be there, like that. So once we know the p-value, then we have a metric to say. When p is greater than 0.10, then the result is not significant. When it is less than 0.10, then it is marginally significant. Okay, but if it is less than 0.05, then it is significant. 90, that is 90 significant at 95% confidence level. When it is less than 0.01, then it is highly significant, because now this is actually at the 99% significance level. So this you can say this is more than 90, less than 90, more than 95, more than 99. So that is how it is. So now since we have already determined in the previous figure the trends for each of the for this location as a function of the year, as a function of season, and also as a function of intervals. One in 2002 to 2009, 10 to 17, and 2 to 17. Now let us try to correlate the correlation coefficient and the p-value that we have got. So I have highlighted here the season or the period with respect to the earlier figure is written here, and what I have written here is the p-value, and these were all AOD values. So p-values for these equations or these trends. So you see, for example, in winter, the p-values are less than 0.05, means they are significant. So how do we do this? When we go back to the previous figure in winter, for example, we say 2010-17 versus 2002 to 17. If you look at the R value, for example, this is 0.75 for the post-monsoon. So the p-value is this 0.03, and if you look at the annual one, the R value is 0.60. Okay. And in the same way, you will see the remaining ones, for example, the p-values are higher, which means that these are statistically not very significant. But when it comes to post-monsoon, it is highly significant. So let us go to the post-monsoon figure. Post-monsoon, you see that the R value is actually 0.81, even higher than this. So you see that this is highly significant. And if you come to the annual, the overall trend is 0.01, p-value is 0.01, which means it is highly significant. Then this is 0.63. So there is a measure of how the trend can be ascertained, whether the trend is valid, valuable, or it is calibrated and can be used to indicate the increase or the decrease reliably. And then so that we can quantify the changes that are occurring over a function of time. So in this practical session, to sum up, we took the case of any atmospheric parameter, and we discussed what is the difference between anomaly and trend. And in trends, for example, the different methodologies that are used to derive the trends, like whether the trend is of additive or multiplicative nature. We discussed the linear regression method, how it is used in general. There are other methods too, but they all follow more or less the same kind of algorithm that I pointed out. And we also saw that depending on whether the data, the uncertainty in the data is a constant, or if it is not a constant one, how it changes, how we assign weights, and then how we determine in what way it changes the trend, the parameter, etc. We saw looking at analyzing the actual data, and then we also saw that the trends can vary as a function of sort of time, season, etc. And it can also change. There can be a change in the magnitude of the trends depending on where it is, because the parameter of which you are trying to determine the trend, whether it is a natural phenomena that is due to the natural phenomena, or any additional input that is happening in the atmosphere, that determines whether the trend will be of uniform magnitude throughout, or it will change as a function of time. And that is what was illustrated by looking at the difference in trends between the temperature versus another quantity, which is contribution by emissions or aerosols, which keep changing as a function of time on a decadal time scale. And then we derived the trend. We found that over the same location, the trend can be different as a function of time and as a function of season. And we also discussed about how the metrics of trend, apart from R, the correlation coefficient, or the R squared, the determinant of the coefficient, how we evaluate the trend, that is, say that this is significant, this is not significant, and this is highly significant. We also see what are the metrics that are used. Typically, the p-value is the one which measures the probability that an observed difference how it would be. We saw that, and then we looked at the quantitative values of the numbers, not only looking at the figures and the trends and the R values, we also ascertained or confirmed this with the p values that we derived for the trends. With this, let me close this practical session. If there are any questions, I'll be happy to answer. Are there any questions? Yes, any question? No question means either everybody understood anything.
Yes, sir.
Or nobody understood anything.
Everybody understood, sir.
Okay.
So thank you very much, sir. On behalf of the organizing committee, we thank Dr. Ramachandran for his wonderful presentation on aerosol as well as the practical sessions, how to analyze the trends of parameters. Thank you, sir. Thank you very much for your nice presentation, sir.
You are welcome. Thank you.
Thanks.
Yeah.
Participants. Participants, please join with us at 2 o'clock. Okay, thank you.